Okay, so I thought my internet connection in my office would be a little bit better, but I do apologize if I go in and out. But I want to thank Nicole for the kind introduction. And today I want to talk to everybody about this idea that Rick and I came up with to address this critical need in developing grid-scale energy storage technologies. And before I talk about this idea, I want to give everyone kind of a global context to describe this need. And here I'm plotting, here's a plot of global temperature change relative to pre-industrial times versus our time. And you can see that our human-induced warming is rapidly approaching this 1.5 degrees centigrade mark, where beyond this point, there's a lot of uncertainty in how it will affect our global climate. And I'm by no means a climate scientist, but there's a clear link between carbon emissions, which is plotted on the left here, and global warming, which is plotted on the left here, on the right. Oops. And so although we cannot say global warming is the cause for any future or specific future natural disaster, we can say it increased the odds. And so this link between carbon emissions and global warming is something that we need to address. And we need to address that by achieving net zero carbon emissions. And so commonly we might hear we might hear a common headline in the media that says, some policy from the government has reduced the carbon footprint of some sector by 17 million tons per year. This is just a random number. And it's equivalent to taking, Z amount of cars off the road per year. And, the initial impression to this statement would be positive, but I have no way of understanding, for example, how many cars off the road per year we would need to address this huge problem of carbon emissions. And I like this framework by, this book by Bill Gates published earlier this year, where he talks about we have to get from 51 billion tons of carbon emissions per year to zero. And that's going to be very difficult because almost all human activities produce some form of carbon emissions and greenhouse gases. And here I'm plotting the various categories that emit greenhouse gases. 31% goes into making things such as cement, steel, and plastic. 27% greenhouse gas emission comes from producing the electricity. 19% from growing things. 16% from getting around the fuels that planes, trains, and trucks and ships use. And 7% for keeping warm. And so there's many solutions being explored to mitigate these greenhouse gas emissions, one of which is using cement as the media to store CO2 instead of emitting it. And the team at UCLA recently won the Carbon X Prize for their venture earlier this year. Solutions like carbon dioxide, capturing emissions directly from power plants or directly from the air. Electrocatalysis to combine clean electrons and catalysts in order to make ammonia for fertilizers or fuels that are clean, and all of these other solutions. And so the point of the slide is to kind of show the scale of this problem of carbon emissions, and that not one magic bullet will be the solution to tackle all of these sectors. But one key solution that has been identified is if we can electrify as many things as we can and get the electricity from clean energy sources. And so by electrifying as many things as we can has impact beyond just this 27 percentile, because we could then electrify our transportation sector, batteries for electric vehicles, for example, or use clean energy to produce some of the fertilizers or fuels that we currently use. And so this is going to require a lot of innovations on the grid scale, how we get electricity and generate it. And the electrical grid is actually a modern marvel, but it was not designed for the intermittent nature of renewable energy sources like solar and wind. Electrical grid basically performs two functions, generation and transmission. And so to generate electricity, you typically will burn things up to heat water to turn some kind of turbine, right? So we can burn things using coal, natural gas, nuclear. And all of these turbines are spinning at the same frequency, right? So in United States, we use 60 hertz, Europe is 50, but all of these turbines are spinning at the same frequency. And I'll emphasize why that's important later on. And this energy gets transmitted. You might have seen these structures driving down the 5 highway here. But these transmission lines also have a maximum current that they can pass before overheating. And that's set by this resistance, okay? And so what exactly happens when we flip on a light switch? Okay, so when we flip on a light switch, we're essentially adding the light bulb circuit to the grid. We're adding a load, and this entire grid is humming at 60 hertz. And so this minimal load will actually seek to decrease the frequency a minimal amount. And this is an alternating current, which is why our light bulb flickers if you have high-speed cameras that capture that. And so this grid is designed for immediate generation of energy as we put on this extra demand on the grid. But intermittency is dangerous with high penetration of renewables, right? So an example would be if we're using solar, if we have too much sun, then we have too much generation, and then this frequency would go up too high. And you can see that you just need a little bit of an increase in frequency to result in equipment damage. And so too much sun is typically why we have sometimes negative pricing of electricity, because we can't just turn off all of the other engines and turbines running at 60 hertz frequency. The other problem is if we have too little of this renewable sunlight at night, where the frequency goes too low, right? And then that would mean that we would need to cut off some of the demand in electricity. And so one way to solve this issue of intermittency is to introduce energy storage on the grid so that we can store energy when it's in excess and provide it when we're in a shortage. And then the challenge then is to understand how to store massive amounts of electricity cheaply and safely. And when I was in grad school, I read this nice review by Dr. Dunn summarizing the many options for grid-scale storage. There's no clear winner yet. And for context, right now, less than 5% of electricity on the grid is stored. And of that stored electricity, 95% is using pumped hydro or dams, right? But dams are geographically limiting. We can't have dams everywhere. And so here's a table from that review paper that summarizes various options for grid-scale energy storage. And what we really need is something that's very cheap, long-lasting, safe, and has high-rate capability to respond to the rapidly changing demand and generation on the grid. And so to give an example, to really highlight the scale of this problem of energy storage at the grid level, if we imagine in the future somewhere, the city of Tokyo is somehow powered by 100% renewable wind energy, but a storm suddenly requires this wind energy to be shut down for a period of 3 days. We would need 14 million batteries at a cost of $400 billion just for the city of Tokyo to provide energy for 3 days. And so this is the equivalent to the global production of batteries over the span of a decade. So you can see kind of the scale of this problem of grid-scale energy storage. And one thing I'll emphasize here is back in 2011, when this review was published, cost of lithium ion was still very expensive. But over the past decade, now it's dropped by an order of magnitude, which gives me a lot of hope in saying that if we this. And so why zinc chemistry, why we want to explore zinc chemistry is quite simple. It's cheap and safe, right? So zinc is much cheaper than lithium, and it's intrinsically safe because it's using aqueous chemistry that's resistant to fire, rather than the flammable organic solvents commonly used in lithium chemistry. Okay, and so there's been a lot of innovation in zinc chemistry on both the anode and cathode side. So on the zinc metal anode side, there's been demonstrations of nanostructuring and electrolyte engineering to mitigate the dendritic growth challenges that zinc metal anode has. And on the cathode side, there's been demonstrations of these transition metal oxide nanostructures that allow for higher capacity, higher amount of zinc being able to be stored. But it's unclear right now what these mechanisms for storage are on the cathode side, which leads me to these remaining challenges that we hope to address in our proposed work. We want to be able to develop a high rate but low cost cathode material that can store zinc at high capacity. And we want to enable the zinc anode to be reversibly operated without dendrite or loss of efficiency. And we also finally want to understand the failure modes and operating principles of how the cathode stores such high capacities, okay? And so our approach really leverages the strengths of Dr. Kaner's group and my group in materials design and characterization. And I'll talk about these two thrusts that we've come up with in order to tackle this problem of grid scale storage. So the hypothesis kind of guiding our first thrust in materials design and engineering is that multivalency in vanadium oxide can enable high capacity storage. And this makes sense because if you have a multivalent and more oxidation states, we can access more redox reactions to enable electron transfer. And our objective is to incorporate multivalent vanadium oxide onto a graphene scaffold in a one-step synthesis. And so here is a schematic demonstrating our proposed synthesis, and where we take precursors of vanadium chloride and graphene oxide and coat them onto a graphite paper. And then using the laser scribing technique pioneered by Dr. Kaner's group, converting these precursors into our composite material of a laser-scribed graphene and a vanadium oxide. And our design principle here is to have these nanoscale vanadium oxide particles embedded in this interpenetrating conductive network. And we can tune parameters such as precursor concentrations, coating thickness, and laser power to achieve the final product. And so some of our preliminary results are shown here where we characterize this material. And the key points to take away from here are the electron microscopy images show that the vanadium oxide is well distributed in this graphene scaffold. And XPS and XRD data show that the vanadium oxide we generate has multiple oxidation states from 2+ vanadium all the way to 5+. So we have presumably access to these higher oxidation states, which can potentially improve capacity. And so when this material is used as a supercapacitor, we have very good rate capability with high energy density relative to other supercapacitors. And as a reminder, for supercapacitor technologies, no electrons are transferred. Instead, there's a double layer, electrical double layer that gets built up in which we store the charge as surface charges, okay? And so we want to see if this material can be optimized as a, to function as a cathode in zinc chemistry. And our preliminary results here show cyclic voltammetry curves between our material and a state-of-the-art material that uses vanadium oxyhydroxide. And the key takeaways from the cyclic voltammetry plot are two takeaways. The first is that the peak current is higher than that of the state-of-the-art, and these mass loadings are approximately the same. So this indicates that we might be able to store more capacity per unit weight using our material. And the second takeaway is that the hysteresis is much lower, the separation between these various peaks, which suggests that we might have less internal resistance due to the graphene scaffold, potentially enabling higher rate capabilities. And so our proposed future work that we'll pursue in this project is to see and test the cycling stability to see if we can get thousands of cycles using our cathode material. And if vanadium oxide doesn't work, we also have the option of using manganese precursors to generate manganese oxides that can also serve as our cathode. So that is part of our risk mitigation in thrust 1. The hypothesis driving our aims in thrust 2 are we want to use advanced characterization in order to determine how these materials store high capacity of zinc, and also eventually how they fail. And so here I want to illustrate these proposed mechanisms for how vanadium oxide stores its capacity and how it eventually fades. So there's been debate in the literature as to whether the capacity comes from an intercalation of these ions or a pseudocapacitance that's a redox restricted to the surface of this material. And then for capacity fade, it's been hypothesized that either there's metal dissolution, vanadium that's going into the electrolyte, or a formation of insulating byproducts that destroy the electrical pathways in this cathode material. And so our objective is to really use our advanced characterization tool to determine the distribution of chemical and structural changes in our vanadium oxide material as we charge and discharge the battery. And the technique we want to use is the cryogenic electron microscopy. This technique we showed is very, very effective in characterizing sensitive battery materials. And so back in my PhD, we were the first to demonstrate this technique for lithium metal anode, where we showed the atomic columns of lithium for the first time, demonstrating that under cryogenic conditions, these sensitive materials are stable under the electron beam. And so this technique has this unique capability to preserve and stabilize battery materials in their native state. And some of the follow-up work that came from this initial demonstration is the ability to preserve liquid-solid interfaces during battery operation. For example, when the cathode material is dissolving into the solution, we want to capture that by preserving this liquid-solid interface. And so I won't go into the details of how we do this, but we essentially take inspiration from structural biology and how they vitrify their samples in making this new discovery of the swelling of a corrosion film that is observed at this liquid-solid interface, again, for the lithium metal anode. And so what we can do using this technique in our proposed work is to characterize this vanadium oxide cathode at various points in the battery's operation and see, for example, if we can observe a lattice expansion in this cathode, which would be expected if intercalation were the mechanism of storage. Or, for example, if we can map out the vanadium in the liquid phase using spectroscopic measurements. And so I want to conclude by thanking the CNSI Nobel Family Innovation Fund in providing this opportunity for a junior faculty like myself to work with a senior faculty in Dr. Kainer. Dr. Kainer has been very supportive, and if you guys know Rick, he has many, many stories that are interesting both within science and beyond. And I also want to thank Dr. Matthew Mecklenburg, who is the director of the EICN facilities, who's been really instrumental in helping us acquire some of these atomic resolution images of lithium metal. So I do want to apologize for my internet breaking down, but I want to thank you everyone for your attention, and we'll be happy to answer any questions.